We're going to talk today about STARKs. This stands for Scalable, Transparent Arguments of Knowledge. And they serve to solve some of the scalability issues that blockchains suffer from. Basically, they are a means to an end. The end is what we call computational integrity, and that allows us to show that we performed a certain calculation in a correct way, and that it can be, in this case, verified much faster than the naive verification, which would be rerunning the whole computation again by the verifier. Yes, so what are the basic steps in STARKs? Well, first we have a computation that we want to prove that we perform correctly, and so we will have to transform it into some STARK-friendly form. We will work with polynomials and their properties to prove the correctness of the computation. And to that end, we will have to work over some finite field, yes, and that finite field has to be STARK-friendly. Normally, we will work with multiplicative subgroups, and we will need that p minus 1 is of the form 2 to the m for some large m times q, where q is an odd prime. In our case, we will choose 17, which is 2 to the 4 plus 1. This is a small number for practical applications, but it would allow us to carry out the calculations by hand. So suppose that we want to perform a calculation. We start with what we call the execution trace. And so suppose we have some registers, T1, T2, TW. We can think of them as the variables we have in the problem. And, well, we have different time steps. For time step 0, we have T11, T12, T1W, and for time 1, time 21, time 22. And so we have a table of this sort. We will deal with a simple example. Suppose that we want to compute the following sequence. We say A0 equals to 3, and then AN plus 1 is equal to AN squared. So what we are doing is calculating the square of the previous number in the sequence. So, for example, the first 4 terms of this sequence are A0 equals 3, A1 equals 9, A2 equals 9 squared, and this is 81, but since we are working with 17 as modulus, well, this is congruent to 13. And then A3 is simply 13 squared, which is congruent to 16. Yes? Now what we will do is interpret this, which will be our only register, as the evaluations of a polynomial over a suitable domain. We could obviously work, for example, saying, well, we have x, we have t of x, and so we can say 0, 1, 2, 3. So we would have like t of x be 3, 9, 13, and 16. But to make our lives easier, we will use the generator of one of the subgroups of the multiplicative group of 17. So we will choose as a generator the number 13. And if you look, when we do 13 to the 0, this is 1. Then 13 to the 1 is 13. 13 squared is 16. 13 cubed is 4. And if we do 13 to the fourth, we go back to 1. So there are 4 elements in this subgroup. And so what we will do is say, okay, for 1 it's 3, for 13 it's 9, for 16 it is 13, and for 4 it is 16. And so we need to find a polynomial taking these 4 values at these 4 points. This is a common problem, which is the interpolation problem. And there is a unique polynomial of degree 3 that passes through these points. One easy way to do interpolation, but by no means practical, is by using the Lagrange polynomial. So we'll say that t of x is L1 of x times what we say is t of 1 plus L2 of x t of 13 plus L3 of x t of 16 plus L4 t of 4. Yes, so Li of x will take the following values. It is 1 when x equals xi, and 0 if x isn't xi for this group. So what we can do is look at the shape of some of these polynomials. And so the first Lagrange polynomial for this particular problem is simply x minus 13, x minus 16, x minus 4. So the polynomial evaluates to 0 in 13, 16, and 4, which is what we wanted, divided by 1 minus 13, 1 minus 16, 1 minus 4. And so this polynomial also evaluates to 1 when we evaluate it at 1. And so, well, if we do the calculations, then L1 of x is simply times t of 1 is simply 5x cubed plus x squared plus x plus 1. Well, if we do all the calculations, then we obtain the trace polynomial t of x, which is 13x cubed plus 2x squared plus 16x plus 6. Yes, you can try for yourself and see that if we evaluate it at 1, that yields 0, and that is the same for, that it evaluates to 3. And, well, if we evaluate it at 13, that gives 9, and so on. And so this polynomial condenses all the information of the execution trace. Well, now what we want to do is to evaluate it on a much larger domain, and that is called a low degree extension. And to that end, we need to find a domain which is much larger than the original domain. So we will select a domain D0, which is equal to beta times the original domain that we used. So our original domain had 4 elements, and this parameter beta is known as the blow-up factor, which tells us how big is the new domain with respect to the previous one. For our example, we will choose simply 2, and so this domain will have 8 elements. Well, so now we have to select an appropriate domain, and we can choose, like in the previous case, a generator, and in this case we could choose 9. And so we can look at the different powers of 9, and we see that whenever we do 9 to the 8, we wrap around and arrive at 1. And, well, obviously 9 to the 0 is 1, and 9 to the k is not equal to 1 for 0 less than k less than 8. The problem is that some elements are contained that were in the original domain, and we want these domains to be disjoint, so to avoid some problems later. So what we do is we are going to shift these elements by taking an element from the coset, and 3 is an element that does not belong to the powers of 9. So our domain will be of the form w times h to the 0, w times h, w times h squared, so on until w h to the 7. And so if we look at these values, this is simply the set 3, 10, 5, 11, 14, 7, 12, and 6. Now, what the prover has to do in order to show that he's doing the right thing is to commit to that polynomial. And the way we do it is the following. First, we generate the LDE for D0, and so we will have like T of 3, T of 10, T of 5, T of 11, until T of 6. And what we are going to do with these values is form what we call a Merkle tree. So we will just, here is T of 3, T of 10, T of 5, T of 11, T of 14, T of 7, and so T of 12, we're going to do this just for the first time. And what this does is takes these two values and produces a hash from these two. It also takes these two and hashes them again. So what we do is at the next level, we have fewer elements. And now we hash again. And again. And so we arrive at this point, which is what we call the root of the Merkle tree. And so if the verifier, the prover, wants to commit to this polynomial, all he has to do is send this root to the verifier. And whenever he wants to send an element belonging to this Merkle tree, say, for example, the value T of 5, then he needs to pass an authentication path, which is given by this element, and this element here. And so he can compute all the way to the root, and if the calculation matches the original root, then this element belongs to the Merkle tree. The properties of the security of the Merkle tree rely, of course, on the properties of the hash function that we are using. For example, we could use SHA-3 or whatever hash function we want. For example, Poseidon is another hash function. So now that the prover has committed to the trace polynomial, what we have to show is that that trace polynomial satisfies the constraints given by the computation. And so we have different types of constraints. First, we have what we call the boundary constraints. And these constraints, what they tell us is that, for example, the value of the trace polynomial equals a certain value, for example, t of 1 equals 3, we started our sequence saying the first value is 3, so we want to enforce that on the calculation. And the other type of constraint is what we call a transition constraint. And so we knew that our sequence is given by the following relation. So we can translate this to a multivariate polynomial p of xy, and that polynomial will evaluate to 0 whenever the constraint is valid. So what we can do is, for example, if we want to say that we are taking some element of the trace, we'll just denote it by t of x. And the way of saying I am going to take the next value is just by doing t of g of x. So if we call this polynomial y minus x squared, then when we do p of t of x, t of gx, and we evaluate this at x in the domain where the constraints hold, that should evaluate to 0. For example, if we do it at 1, at 3, or at 16. If we do it at 4, there is no next element, so the constraint will not be valid. So how can we show that the constraints are in fact enforced? This will depend on the property of polynomials, which says that if our polynomial p evaluated at some point a equals b, then this means that when we take our polynomial and we subtract it by b, is divisible by x minus a. Yes, another way of saying it is that p of x minus b divided by x minus a is a polynomial. If the constraint doesn't hold, then this function defined here then this is not a polynomial. So we will see how to deal with this, and we will start with the easiest one, which is the boundary constraint. So in this case, what we are going to do is generate a polynomial p1 of x, which is simply the trace polynomial minus 3. Of course, we can see that if we do p of 1, this is t of 1 minus 3, and this is obviously 0. So this means that t of x minus 3 is something like x minus 1 times another polynomial. So, well, we can calculate p of x, and in this case it is 13x cubed plus 2x squared plus 16x plus 3. And well, we can then divide p1 by the vanishing polynomial where the constraint holds, which is in this case just x minus 1. And so the polynomial is 13x squared plus 9x plus 5, which is a polynomial as we expected because the constraint holds. Well, now we can move to the other constraint, which is the transition constraints. In general, for some problems, we will have more than one transition constraint, but the procedure is the same. So let us focus on the transition constraint. And so what we are going to do is we are just going to generate P2 of x, where we will compose the transition constraint polynomial with the trace polynomial so as to enforce it on the trace. And so this would be like t of 13x minus t of x squared. And so if we do the calculations, this is a degree 6 polynomial because the original polynomial was degree 3, and then we take a square, so we get that value. And so this is the form of this polynomial. And so, well, we can check that, of course, if we do P2 of 1, this is the same as P2 of 13, and this is the same as P2 of 16, and this equals 0. So what this means is that P2 of x should be of the form x minus 1, x minus 13, x minus 16 times some other polynomial. So what we will do is the same as before. We are going to divide the polynomial by the vanishing polynomial where the constraints hold and obtain another polynomial. So this is P2 of x divided by Z2 of x, which contains these three terms. It is the product of those terms. So it vanishes at 1, 13, and 16, which is where the constraint holds. And so if we do the calculation, we get the following polynomial: x cubed plus 12x squared plus 9x plus 16. And so we have all our constraints. What we want to show is that each of these is a polynomial. Of course, we know it, but we need to convince the prover, the verifier, that they are in fact polynomials. So what we are going to do is compose the constraints into a single polynomial. That is because if we perform a random linear combination of the constraints, then if both are polynomial, they are polynomial. But if at least one of them is rational, then the result is very unlikely to be a polynomial. And so we define the following polynomial, where we will sample some random values. And so this will be C1 of x times a random number alpha times a degree adjusting term, so that this polynomial has degree d, plus beta 1 plus C2 of x alpha 2 x d minus d2 plus beta 2. So what we did is just compressed all the constraints into one polynomial. And now we would like to show that this is in fact well done. So, well, for this case, we will sample alpha 1 equals 1, beta 1 equals 3, alpha 2 equals 2, and beta 2 equals 4. These values are generated by the verifier, but when we turn this protocol non-interactive, these are obtained via the Fiat-Shamir transformation. Well, if we operate a little bit, we will get some composition polynomial, which looks like this: 15x to the 4 plus 9x cubed plus 11x plus 4. We can split this polynomial into odd powers and even powers. So we can say that this is h1 of x squared, which is simply 15 x to the 4 plus 4, and h2 of x squared, which is 9x squared plus 11, so that x of h is simply h1 of x squared plus x, h2 of x squared. And now we would like to commit to these polynomials so that we cannot cheat the verifier and show them that, okay, this is my polynomial I got from the constraints, and I am not going to change it. And so what we do is, once again, we are going to evaluate it on a domain. The only thing is, well, now our domain is some t prime, which is simply x squared, so that, well, x belongs to the original d0. And this domain is simply 3, 10, 5, and 11. And so what we do is, once again, we form our Merkle tree, x1 of 3, h1 of 3, h1 of 10, h1 of 5, h1 of 11, and once again we hash taking two values, and then we get the root, and then this we can send it to the verifier so that he knows we are not cheating. That we do the same for h2. Well, what we would like to show is that there is in fact a relationship between the execution trace polynomial and the constraints and the polynomial h of x. And to check that consistency, what we are going to do is sample z, which is outside dt, which is the interpolation domain, and d0. So for our particular case, the only possibilities is that z belongs to 2, 8, 9, and 15. So the verifier will sample one of these elements and tell the prover, okay, tell me the value of the polynomial and the trace polynomial at this z. And so say that, for example, the verifier samples z equals 8. And so to be able to calculate the composition polynomial from the trace, we not only need t of z, but we also need t of g of z, which is t of 13 times 8, which, well, is simply, in this case, 2. And so, well, what the prover is going to say is, okay, h evaluated at 8 is 10, and so, well, h1 of 8 squared is 6, and h2 of 8 squared is 9. And, well, the trace polynomial at 8 is simply 16, and the trace polynomial at 2 is simply 14. And from this information, the verifier should be able to check that there is a relationship between these trace elements, or what the prover claims are the evaluations of the trace polynomial, and what he claims is the evaluation of the composition polynomial. Then we will have to devise a method to prevent the prover from cheating and sending us random values. So why does the verifier need this? Well, we can show it by explaining how the verifier is going to check that relationship. And so this is what we would call the verifiers work. So the first step is, well, he can evaluate what we call P1 at 8, which is simply T of 8 minus 3, and this is simply 13. He also knows where the constraints hold, so he can evaluate the verifier. So C1 of 8 is simply 8 minus 1. Remember, this is simply because it was x minus 1, and this is 7. So, well, he can now compute the quotient, and this is an operation not in terms of polynomials, but in terms of field elements. And, well, so he gets 14, and of course then what he can do is adjust the degree by doing 1 times 8 squared plus 3, and so this gives 3. And so, well, if we want to calculate the second polynomial at 8, this is t of 2, which was t of g of x, minus t of 8 squared. Just remember this is t of gx minus t of x squared, and this is 13. Then, of course, we can evaluate the verifier at 8, which is 8 minus 1, 8 minus 13, 8 minus 16, and that gives us 8. And so we can, of course, evaluate C2 of 8, which is P2 of 8 divided by C2 of 8, which is, again, 8. And then, of course, we can adjust the degree once more. 2 times 8 plus 4, this is 7. And so we can now do C1 of 8 plus C2 of 8, and this is 3 plus 7, which is 10, and this just matches the evaluation of h of 10. So what we showed is that the trace and the composition polynomial are related. Now, the problem is, how do we know that those values are really the evaluations of the polynomials and that the prover is not cheating? Because he could send any values that fulfill the calculations. And so what we're going to do again is use this trick that if a polynomial evaluates at some point to b, then p minus b should be divisible by x minus the point that we used. And so what we are going to do is create what we call the deep composition polynomial. And the idea is more or less the same. We will call this P0 of x. And this is simply, we will take a random linear combination of different polynomials. This is simply t of x minus the value that the prover claims is the evaluation of the trace polynomial divided by x minus z, plus gamma 2. Now we have to show that it also evaluates to the claimed value of z times g. So then the denominator is now c times g. And we also have the claimed evaluations of h1 and h2. So what we do is h1 of x squared minus h1 of z squared is simply x minus z squared. And we also have this one. So if the prover isn't cheating, then each of these terms is a polynomial. And so the random linear combination is a polynomial. well, we can, of course, calculate each of these terms just so that you can later follow the calculations. The first polynomial is t of x minus t of 8 over x minus 8. And this is simply 13x squared plus 16x plus 5. Then, of course, we have t of x minus t of g of z divided by x minus gz, and this is simply 13x squared plus 10x plus 16. And then we have also these other polynomials, and this is 15x plus 15, x plus 8, x plus 2, and h2 of x squared minus h2 of x of c squared, which is 8 squared, x minus 8 squared. This is 9 times x plus 8. So each of them is in fact a polynomial, and that is because we are doing the calculations properly. Of course, if we are cheating, then some of these terms will not be a polynomial. To make things easier, we are going to say that the verifier sampled random values, but in this case, we are just going to say that they are all equal to 1. And so the decomposition polynomial P0 of x is simply 15x cubed plus 15x plus 1. And so now the prover has to convince the verifier that this is indeed a polynomial. And what we will do instead of proving that this is a polynomial is that we're going to show that this function is close to a low-degree polynomial. And to do so, what we're going to use is something called FRI, which stands for Fast Read Solomon IOP, and IOP is Interactive Oracle Proof. So what we are going to do is, by using FRI, reduce the degree of this function and then apply it again and obtain a function with a lower degree, and so on until we get if this is a polynomial, a constant degree polynomial. And there we end because we just show that it is close to a low degree polynomial. And so, well, to use FRI, the first thing we have to do is commit to the polynomial so that they can tell we are cheating and change the polynomial at the end. So what we are going to do is take d0 again, and so consider all the evaluations of p of x such that x belongs to d0, form the Merkle tree, and of course send the root belonging to the tree of p0. Now that we did this, what we need is to get some way of cutting the degree of our original polynomial. So what we are going to do is split the polynomial between odd powers and even powers. So if we do this, well, then we have p0 even, and well, in this case, it is simply 1, and well, of x, and we can say that, well, x times p0 odd of x is simply 15x cubed plus 15x. So p0 odd is a function of x squared, which is simply 15x squared plus 15, and we will say that x squared is simply y, so this is how it looks. So now what the prover is going to do is randomly fold these two polynomials. And so he will ask the verifier for a value beta 0. And so he's going to calculate P1 of y, which is simply equal to x squared, which is simply P0 even of y plus beta 0 P0 odd of y. And so if we do this calculation, P1 of y is simply 9y plus 10. And so what we see is that we divided by 2 the original degree of the polynomial. And so we can now repeat this process again and again until we reach a constant polynomial. So now that we reach this point, of course, what we are going to do is we will have a domain of the form x squared such that x belongs to d0. And so the domain is reduced. This domain is simply 9, 15, 8, and 2. This is because of the 8 elements. They are related by x, one being x and the other being minus x. So when we take the square, we get the same value. And so we only have these 4 values. So now that we have P1, we can do the same. We can perform the log degree extension by evaluating over D1 and generating a Merkle tree and sending the root of D1. And now we can apply phi once again to arrive to a new polynomial. So this time y P1 odd is simply 9y and of y, and P1 even of y is simply 10. So now the verifier samples beta 1, and so we can now, well, in the previous example, beta 0 was equal to 4, and say now we get 3. And so P2 of z, which is y squared, is simply 3. And so we arrived at a constant polynomial, and so we can stop, and the prover sends this value to the verifier. And well, the new domain is halved, and so, well, the new domain would be simply 13, 4. But we are not interested in evaluating the polynomial since this is a constant polynomial. And so the prover has done the Frey folding, but now he has to convince that he did all the calculations correctly. So he has to allow the verifier to check all these things. So what we will have is have the verifier chooses some value in D0. And for example, he could say, I want x to be 10, which was one of the elements that we originally had. And so what we have is, of course, the evaluations of the trace polynomials. Then, of course, we have the evaluation of P0 of x. These are the evaluations of the composition polynomial at D0. And then, of course, what we have are the elements, in this case, of P1 of x, or well, P1 of y, if we want to call it properly. And then we have, of course, the evaluations of P2 of x. And so when he chose 10, he chose, for example, this value. And so from those values, he has to show that we arrived at a constant polynomial. So in order to do so, what we need to do is take not only this value, but this other value. And these values together will allow us to calculate, for example, the value here. And then if we have some value, another value, then we can show this. And in that way, we're showing that each of the layers was computed correctly from the previous one. And well, we also need to show that there is a relationship between the trace polynomials and the composition polynomial. And so, well, we will have to sample also some values from which to calculate the composition polynomial. So if all these checks are valid, then the protocol was carried out correctly and the proof is valid. So the prover will have to send, of course, all these elements that we showed here, and this will be the elements composing the proof. The only thing is that whenever we pass an element belonging to a Merkle tree, we have to show that the element is also in the Merkle tree. So for each point, we need what we call the authentication path, which allows us to prove that the element is in fact in that Merkle tree. If not, we are passing just random values. And so, just to give you an idea of the proof and the steps in the Frey layers, what we can do is, well, show what things the prover needs to pass to the verifier. And so from P0 of x, he needs to pass the values P0 at 10 and P0 at 7. These evaluations are simply 4 and 15 plus their authentication paths. Then from P1 of x, we need P1 at 15, which is 9, and P1 at 2, which is 11, plus the authentication paths. And well, from P2 of x, we only have the constant value, which is equal to 3. Of course, one thing the verifier needs to do when he has these values is check that they belong to the Merkle tree by checking with the authentication paths. And so how can, from this information, we know that we can do all these jumps? So the formula to check this is given by what we call the collinearity checks. And so pi plus 1 evaluated at x squared is simply pi at x plus pi at minus x divided by 2 plus beta I pi of x minus pi at minus x divided by 2x. And so, for example, we have this value which we will call u, which is p0 of 10 plus p0 of 7 divided by 2 plus beta. For our first step, we said it was 4. So it is p0 of 10 minus p0 of 7 divided 2 times 10. And if we do all these calculations, this is equal to 16. And this value is also equal to P1 of 15, which was this value. So we took two values from the upper layer and we got the same value in the lower layer. So now we can go again and calculate B, which is simply P1 of y minus P1 at minus y divided by 2 plus beta 1 P1 of y minus P1 at minus y divided by 2y. And so for our case, this is simply P1 at 15 plus P1 at 2 divided by 2 plus 3 P1 at 15 minus P1 at 2 divided by 2 times 15 times beta 1, which is 3. And if we look and do the calculations, this is equal to 3. But we also had that P2 evaluated at 4 is 3. This is easy because it is a constant polynomial. And so this value matches this other value. So for this particular choice of the verifier, we show that all the Frey layers are correctly linked. Of course, this could be some lucky choice for the prover, so we can repeat it for other x in D0. And if these checks pass again and again and again, then we can be sure that the prover is doing the things correctly. So, well, you can follow some more examples of Starks at the Stark 101 tutorial. We have an implementation in Rust. You can also follow our explanations in our blog post, natomonadtutorial.com. So thank you very much for being with us here and hope you enjoyed it. Bye-bye.
Genio.